All right, I think you welcome everyone to the world lecture, and I'm really happy, and it's a pleasure for me to introduce and welcome Professor Manolis Veveakis from Duke University. So I just would like to start with a kind of a short snapshot of his academic career, his path, academic path. So Manolis got his degree, 3 degrees from the National Technical University of Athens. First a BS in applied mathematics and physics, an MS in physics, in applied mechanics, and a PhD in geomechanics. And after he got his PhD in 2010, he went to Australia, to Perth, where he started his career there as a research scientist with CSIRO in the Division of Earth Science and Resource Engineering. After a few years, in 2014, he moved to Sydney to get a position, an academic position at the University of New South Wales, where he stayed there for a few years. And at the end of his stay in Sydney, he was a senior lecturer in the Australian system. This is about the same as an tenured associate professor. And somehow he was enticed to go to Duke University, living the beautiful way of life of Australia. But for some reason he went to the US and then started as an associate professor, and now he's a newly minted professor that was announced about a few months ago. The research of Manolis is very diverse. It covers thermodynamics, irreversible processes, rheology of geomaterials, fluid-solid interaction, and so on. And what I want to say is that the impact that Manolis has in engineering and science, for me is measured by the number of students that he has graduated and now holds an academic position in Europe and the US. So he has, over his academic career, which is about 12 years now, has had 6 former students, in academic position, which is quite absolutely remarkable. So he's also editor-in-chief of the Geomechanics for Energy and the Environment. And so I'd like to finish this introduction by a more kind of connection between Manolis and the department. So Manolis was the last student of Ioannis Vardoulakis, and many of you would know that he was a faculty in our department from 1980 to 1990, before going back to Athens to take a position at the National Technical University of Athens. And as you may know, that he tragically had disappeared in 2009 as a terrible accident that happened at home. But that was this connection. And there's another connection is that Ioannis start that topic about frictional heating that as we are going to hear today. And it was my privilege to introduce him 16 years ago. He gave a lecture in Perth at CSIRO exactly on this topic. So I'm very happy to hear the continuation of the story. So please join me to welcome Professor Veveakis.
Well, thank you very much, Emmanuel, and thank you very much for having me here. This indeed has the potential of becoming a very emotional talk, so I'm going to try and keep it scientific for as much as I can. This is a topic that dates back to my PhD, and it holds a special place both in my research program and in my heart. And I haven't presented this topic extensively. I haven't presented that topic ever after Vardoulakis passed. So I was holding it for you. For this one, I have given snippets of this presentation, but never as a whole. All right, so let's dive in before we get emotional. So as a soft introduction to the topic for essentially our young colleagues, landslides is one of the major natural or man-made hazards that we are concerned in engineering. They are ubiquitous, as you can see here from this global risk map, and they have disproportional casualties in densely populated and underdeveloped countries. So as engineers, we have been striving to understand landslides since civil engineering, essentially, was founded. And we are at the point where we can start offering solutions. So let's start understanding slowly at the beginning what and why we bother. And then as we progress, I'm going to start building our modeling capabilities and field applications. So the vast majority of landslides we have analyzed with my former student, Carolina Segisi, has analyzed data from the NASA portal for about 14,000 landslides in the last decade. The vast majority of them, the overwhelming majority, around 70% of the times, they are triggered by groundwater level variations, right? This dwarfs all other effects like earthquakes or excavations, etc. So right from the bat, this calls from us understanding this correlation between landslide triggering essentially and groundwater variations. The reason we are working on that area is that unlike all other natural hazards, this is a study done for Spain, but it's extrapolatable around the world. What you see here is that essentially losses, landslide losses, so in purple the bars are the losses that we expect essentially from these natural hazards. Erosion is liquefaction and sinkholes basically. In orange, you see what are the losses when you develop and deploy preventative measures, and then in yellow is the cost of the preventive measures. So what this means is that among all the natural hazards, landslides are the ones that if we develop relatively cheap preventative measures, they actually work. Okay, that's what it means, all right? So it is worth our time and effort in doing that. All right, and the deployment of preventative measures itself hinges upon our ability to actually understand, all right, to understand the response of the landslides, forecast and control the response of the landslides to external loading like groundwater variations that we saw on the slide before, all right? So that's the conceptual background of the work. In this talk, I'm going to focus on one particular type of landslides, which is the least constrained, least understood, and most devastating type of landslides, and that is the type of deep-seated landslides. So what you see here is a case study from Japan in 2004. Deep-seated landslides are slope failures that are deeply rooted, so the sliding surface is tens or hundreds of meters depth, typically below the groundwater level. And they tend to slide at inappreciable rates. Manuel, can we dim the lights? Yeah. No.
No, I got it.
All right. So what you see is that they tend to creep at inappreciable rates for years or decades, all right, before accelerating drastically and collapsing, taking down entire infrastructure and causing casualties. This is the type of landslides that if you try to develop preventative measures, you will see them here. Wait for it here. There it is. If you develop preventative measures, they will go down with the landslide. All right. So that doesn't work. This is the part of our world that it doesn't work, and we need to understand. All right. So these landslides have anecdotal, let's say, experiential evidence that they follow the typical creep evolution, where it goes through the classical 3 stages of creep. So you have an initial stage where the landslide gets started. Then you have a secondary creep where the landslide creeps at inappreciable rates and can stay there forever. Okay, this is the equivalent of a critical state in geomechanics. All right, and then sometimes it doesn't, and it accelerates drastically to a parabolic, essentially, velocity increase over time and the final collapse. So our early attempts in understanding and forecasting were purely phenomenological, all right? So this started in 1985. You will be surprised or not if I tell you this is current state of the art in the industry. So we went from the experiential, anecdotal understanding that we have transitioned to tertiary creep and this parabolic increase of the velocity in finite time into quantifying it. So we get velocity data. We plot the inverse of the velocity here over time. I'm sorry for the poor quality. The inverse velocity over time. So when velocity goes to infinity in tertiary creep, the inverse velocity goes to 0. All right? So we're looking in the data for linear trends. When a linear trend is established, we extrapolate. When it crosses the axis, inverse velocity goes to 0. We call that failure. All right? So we have a prediction, if you like. So good news, it sometimes works. Gives you a couple of hours at best notice. Bad news, more often than not, it doesn't. It doesn't work. Okay? It has strong limitations, and even if it does work, it has strong limitations. This is a purely phenomenological model. There are no physics in there. You may as well be plotting like the stock price. There is no physical meaning in the data you are handling. And as such, it cannot offer any insight on the origins of failure, cannot tell us where we should go and look out, and it does not give us any information on where, preventing. How can we prevent that? All right? However, it's a first step. Okay? And the second step is saying, okay, let's move on one step further and add a bit more physics. We have discussed that more than 70% of the landslide depend on the groundwater level. So let's add the groundwater level. All right? Let's take the velocity and add the dependence, or a correlation. It's a very popular word. Between the velocity and the pore pressure, and the water pressure, water level. Sorry, same thing. So we know how to do that in geotechnical engineering. If we know one thing, is how to calculate hydraulic heads. Okay? You never heard that from me. But that we do know. Okay? So this is an example from the Vallcebre landslide in East Pyrenees in Spain that was essentially curated by Corominas, Moya, and collaborators, where they just did exactly what I said. They drew a correlation from observations between velocity and depth of groundwater level. Now, this is a bit counterintuitive, because I did say that we know how to calculate hydraulic head, but none of us would take the datum on the surface. They did. So this is a bit inverse. So low depth of groundwater level means the water is at the surface, so you have high water pressures. So if you want to make it intuitive, flip it. It's like that. Okay? So low values of the groundwater level and water pressure means low velocities, high values, high velocities. There is a positive correlation. All right? So if you take that positive correlation and feed it into a classical mechanistic or mechanical model, it works. You can reproduce the history of that landslide for over 2 years. Case solved, problem solved. I'm out. It's slide 7. Thank you very much for being here today. Okay. Now, all right. Obviously, I'm kidding and I'm exaggerating. So for the students, especially among us, there is no such thing as validating a theory. You can have infinite case studies and examples that work, but you only need one counterexample to falsify a theory. All right? And I have 2 to show you why this doesn't work. All right? So here are 2 counterexamples where the positive velocity groundwater level correlation doesn't work. All right? So this, on the left-hand side, is the Vallon landslide. On the right-hand side is the Mud Creek landslide, Italy, California. We'll see them down the road today. Both of them experienced a prolonged period of positive correlation between water level and displacement velocity over 2 years. You see here, it's direct one-to-one correlation. All right? Until the very last stages, where suddenly something happened and they flipped. All right? And they both failed with decreasing value of the water level. All right? So when you have that, this is a telltale that you're not accounting for the physics, for all the physics of the problem. Okay? That something, there's a sudden response, a change of response that you're not factoring in. All right? And in this case, it's quite straightforward to understand what it is. We never opened the black box and actually told the model that this is a landslide. We never accounted for the internal kinematics, internal response of the landslide. We don't know if this is an elastic block, a plastic block. You know, we have never discussed what are we talking about here. All right. So as a summary, I'm gonna summarize these outcomes while I let you enjoy a disaster waiting to happen in Josimath in India. This is a UNESCO site, by the way, that is coming down. So there you go. So in summary. So purely data-driven or mechanistic models could work, but we need to acknowledge their limited applicability. They can never predict change of response, right? Sudden change of response. The data-driven models don't have the physics, to predict a change of response, which is needed if we are to forecast actual failure. Okay? The second observation is that we also kind of know what we're missing. That's the good news. Even if it doesn't work, it does tell us a few things. So we kind of know that we're missing detailed information from the internal response of the landslide to external variations. Right? We don't know how the material responds to external loading. So what I'm going to do in the next half an hour, I'm going to introduce you to such a model, such an approach, where we're trying to put the basics of the internal response of the landslides together with what we have already seen, the external groundwater level variations, okay, and see if we can give some more, let's say, useful predictions. All right, so here comes the hero of our story. This is Ioannis Vardoulakis, who, yes, he was my advisor and Euripides' advisor. And he realized all these things early 1990s. And he started working on concepts on how to create such models. So a bit of historic context. I'm going to swap hats. I'm going to change. I'm going to take my professor's hat out, and I'm going to put my student hat in. OK, I was there. So back then, he was in Athens, and he was coming out of the 20-year study of the shear banding and localization, et cetera. So his mindset was advanced like that. All right. So after working for several years on that, he published a couple of papers. The first papers that tackle the topic on the catastrophic, essentially, evolution of landslides due to frictional heating. Now, for those of us who knew Ioannis, when there is a breakthrough coming, his papers are featuring two distinctive features. Sorry, presenting two distinctive features. Extremely bad graphics, like very low quality graphics, and I'm not done. and way too many equations. Okay? However, don't let these features belie the ingenuity of what's coming here. So what he suggested is a post-bifurcation, post-shear band localization model. Right? So in his mind, he dissected the landslide. This is a cross-section of a typical landslide, if you like. It's a line, but it's a landslide for us. All right? So he imagined a fully developed shear band on critical state. All right? So it's at the base of that. And he imagined an extension to the classical frictional slider model. All right? So there is a rigid block slide that is doing nothing but sliding. All right? Sliding on top of a shear band that is fully developed at critical state and receiving, essentially admitting all the deformation. All right? The initial form of the equations he wrote, these are not random equations, by the way. These are the governing laws of physics. All right? This is mass balance, energy balance, momentum balance. All right? However, I think the ingenuity was not in the poor sketch here. The ingenuity is that the equations are not applied equally on both domains. The sliding block is taking care of momentum, right? Because the shear band is too thin to understand inertia. And the shear band takes care, and water level, and the shear band takes care of energy balance, dissipation, and deformation, all right? So, and the two talk through their common interface by standard localization concept of assuming continuity of the fields, not the fluxes, right? So the stresses are continuous, the temperature is continuous, the pressure is continuous, okay? So that's the ingenuity. His first versions on these papers, his first versions of the model were extremely focused on the late dynamic weakening states, right? So, post-tertiary creep. And the mathematically enterprising among you may understand that because this system does not have a steady state. So this system, the steady state that this system has is the landslide being at rest. So the landslide is either at rest or it dynamically weakens from critical state to residual state. All right? So he understood that, he knew that, and right from the beginning he was working into an extended version of these concepts to have essentially a friction coefficient that can admit critical state, all right? That can sustain a constant value for prolonged periods of deformation. So These concepts led to another paper in 2002, which I was fortunate enough to see in a preprint stage, because this is where I was starting with him in his lab as an undergrad. In that one, he suggested friction coefficient as a function of two counterbalancing mechanisms. All right? So he said most clays exhibit velocity hardening. So I'm going to have my friction coefficient harden with velocity or strain rate. At the same time, I need a softening mechanism to counterbalance. He tried a few. He tried strain softening. He has tried that, but then he realized that there is no way. This is not linearly independent. Have strain and its rate counterbalancing. So he went to another field, which is temperature. I'm sure I'm going to get asked this question, why temperature? I'm going to hold until the Q&A session. So the two are put together, hardening against softening, so that at critical state, they can counterbalance and have a constant value. All right? Now, I was an undergrad when I was asked to do a final proof check of the preprint, and the blood drew out of my head when I saw him fitting a highly nonlinear curve from 2 data points, with one data point being, you know that this was coming, with one data point being the 0. All right? But as you will see towards the end of the talk, he was right. He was right. All right? And when I told him, he's like, it's not 2 points, it's 3, because we know that in finite time we cannot have infinite friction, so it has to be like this. And I'm like, okay, whatever. All right. So I took this model and put it into the test, and I analyzed. So this is a paper that we published in 2007. So for PhD students among us, when you publish your first paper, make sure you spell your name right, because I misspelled mine. And that is still haunting me. All right? So please make sure you spell your name. All right, so what we did, this is the Vaillon landslide. And we did the opposite from what you saw from Korominas. We kept the groundwater level constant. All right, so in the Koromina study, the groundwater level was varying and the internal response was constant. We did the opposite. We fixed the groundwater level at a given constant level. All right, and then we used that model. I will show you how. And then we were able to reproduce the final 7 months of the landslide. Now, this latest version could capture, so this can capture transition from secondary to tertiary creep. The model has it in it. All right, we didn't know back then why. I'll show you why. Okay, but the model has this transition in it. The problem that this model still has is that there is no varying groundwater level. So there is no way you can capture deceleration with this model, because this model just accelerates, right? So just before his accident, I was in the process of bringing the two together. So saying, okay, that's a slam dunk case, right? I have the internal response without groundwater. I have the groundwater without internal response. I'm a mathematician. Okay, let's bring the two together. Never happened. Life happened. I'm putting back my professor hat, and I stopped working on that for 10 years. All right, that's how bad it was. And when I went to Duke, my first student had somehow an obsession in working on landslides, and she convinced me. So that was Carolina Segui. She convinced me on dusting off my notes. And I was wrong back then, so we fixed it. So this is how we did it. All right, so this is the model of bringing both together. What you see here, is a schematic. I'm going to go through a schematic representation. There is no point in bombarding you with equations. So what's happening is we take the groundwater model in a classical geological field scale. All right. From that, we calculate this is the mass balance. From that, we calculate the hydraulic head, feed it into a limit analysis or any other software you may want, classical geotechnical things. We calculate the stresses, feed them into the shear band. The shear band should respond to the external stresses. We calculate the velocity from Vardoulakis' friction model in here, and we return it back to the field scale. That's it. That's all. Okay? So everything hinges upon solving the equations in here. Everything else is standard cookie cutter. No challenges. All right? So the equations in here are easy, but also counterintuitive. So if you write the momentum balance in here, because the shear band is very thin compared to the overburden, you will never have inertia. What you will get is stress equilibrium. So the stresses, the shear and normal stresses, are homogeneous inside the shear band, homogeneous, same value, and equal to the outside stresses that you calculated through the groundwater level. Okay? There is no mass balance because the initial state is critical state, so there is no excess pore fluid pressure or volume changes. Okay? And the only equation that survives is the energy balance. The energy balance featuring heat capacity, temperature, thermal conductivity, and the dissipation in shear, because you only have shear. Okay? So if you take that together with Vardoulakis' friction law, you can solve for gamma dot, obtain that, feed it in here, and you have a closed equation mathematically for temperature that features the external stresses that you calculated. So you could feed the stresses from the outside and get the response of that from this equation, right? Clear. Now, if it gets simpler than that, all right? If you do some basic dimensional analysis calculations, you can reduce this equation into that, which is a single parameter equation. This is all dimensionless. Okay, there is a single parameter here called the GR from Greece, from Grunfest. So Grunfest did a seminal work on viscous flow for thermally sensitive materials back in 1963. This number is a parameter group. It incorporates all the material and boundary properties of the problem. Okay, thermal sensitivity, rate sensitivity, external stresses, initial strain rate, thermal conductivity, shear band thickness. Everything is in there, okay? But it's a single parameter model. The physical meaning of this Grunfest number is relatively simple. It's a ratio of two rates, if you like. Okay, so it's how fast you produce heat due to friction versus how fast your material diffuses that heat away. When this is zero, when this is small, you are producing frictional heat slower than the material can diffuse away, so the material always has time to dump heat away and stay at the quasi-isothermal limit. When this is large, you're producing heat faster than the material can dump away, so you are entering into an unstable adiabatic regime. All right, so if you want like visual aids, imagine rubbing your hands. If you rub them too slowly, you don't feel anything, because the heat that is produced gets out. If you rub them quickly, you start feeling the heat. That's what this number represents. Okay? Now, everything I said can be plotted in a very elegant mathematical way if you just run a simple bifurcation analysis. Doesn't like me. All right? So what you see here is the steady state, so this one equals to 0, solution of temperature, the norm of temperature, versus the Grunfest number. All right? So what you see is a classical fold bifurcation for those who are mathematically inclined. For those of us who are not, this is a two-branch solution. This is a stable branch. This is an unstable branch. If your initial condition lies in here, your landslide will stay stable. If you go out there, your landslide will go unstable and experience what is known as a thermal runaway instability. Let me show you how it works. All right? So let's consider two initial conditions here. Same initial condition, slightly different Grunfest numbers. All right? This one starts in here. This in this gray area, stable area. This one starts outside. So what you will see if you take these initial conditions and run this equation is both of them starting here, going at that point, which is roughly that one. The pink one, point 1, will admit this branch and stay there forever. Okay? The other one will just go in thermal runaway. Okay? You can also plot the velocities, because the velocity is just the logarithm of temperature, or the other way around, I don't remember. That is the velocity. Okay? So the velocities follow exactly the same. All right? So this one, remember, in principle, is not constant, because it has all the external dependency on the groundwater level. Okay? So what you see here is a bifurcation or stability plot of external loading versus internal response. Okay? So the claim that I'm going to make is that as long as your landslide stays in this area, the landslide as a body is stable and prone to remediation measures. Okay, the moment it goes out, it gets tougher. It becomes unstable. Okay, so that's the claim. Let's start testing it. The first case study that I'm going to talk about is the Vajont landslide. This is a landslide that happened up here in the Italian Dolomites, about 70 miles north of Venice. Okay, and what happened was, you see a picture of it today. Okay, what happened was that the mountain, after 2 or 3 years of creep, fell into a reservoir behind a dam that still stands. Shout out to the structural engineers, by the way. All right, it fell with a velocity of about 120 kilometers per hour, which is what, 70 miles per hour? Okay, so remember that I'm going to play a video, which is an artistic rendition of what happened here, which is viewed from that side. You can see the dam is here. So what happened right after this collapse was unexpected. So that happened in October 1963. The mountain fell in the lake, and that with 120 kilometers per hour, that caused a tsunami wave to overtop the dam, flood the downstream valley, and kill 2,000 people. This is, to date, the deadliest human-induced disaster in civil engineering, basically. Okay? But the dam stands. But the dam stands. All right? At least we didn't have a dam failure that would have flooded the valley. All right. So let's go and test the model. It is a loaded slide, so hear me through. You see 3 panels. This panel is the input data. These are the real field data from the Vajont study. This is the precipitation, reservoir level, velocity. Okay? Reservoir level is essentially the groundwater level here. In the middle, you see the real field data in blue dots against the model velocity within an uncertainty cone, because we don't have access to all the material information. It's a landslide that happened 60 plus years ago. And the calculation of the model temperature that comes out as a bonus, because we calculated why not plotting it. And then on the right-hand side, I have plotted this solution, the best fit, on the phase space. Okay? So what we're going to do is we're going to track it. So you calculate the reservoir level. From that, you run a standard geotechnical model, calculate the stresses, feed them into Grunfest, blah, 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 blah. All right, so let's talk. The dam was finished after bypass tunnels and safety measures towards the end of 1961. So this is where we start our story. So the engineers started filling the reservoir here. Immediately after they filled it, the velocity started increasing. Okay? So if you map that on our phase space, we start down here, very stable, and then we just go slightly up, but still in the stable area. We're just tracking the stable branch. Okay? Then they were alerted here. They wanted to test the positive velocity water level correlation. So they brought the groundwater level down, the reservoir level down. The velocity came down as well. The phase space came down. Super. Good job. Okay? Shout out. We got this. Let's go to the design threshold. All right? So they increased it to the design threshold, which was 710 meters. Then landslides started accelerating again, but not in dissimilar values. They were pretty much the same values as before. Okay? However, this time they went a bit too far. They didn't know it. Okay? But now in hindsight, they went a bit too far and they exceeded. They went out of the stability area. All right? So that had as a result the landslide becoming unresponsive. So when they lowered, they saw the acceleration and then they lowered the water level. However, the landslide. Okay? So I can run an inversion and give you material parameters and kind of mix and match them with what knowledge we have, but I don't even believe in this inversion. All right? So I will not even bother here. However, the model performs relatively well, okay, whatever that means. But, you know, this was over 60 years ago. I cannot tell you that I have predicted the Vajont failure 60 plus years later, okay? And there is no convincing way to get access to material properties that we need, like thermal sensitivity, rate sensitivity, et cetera, et cetera. There are a handful of experimental studies that have been performed but they are all in the post-tertiary regime. They are very fast. Okay, so they're not representative of what we need. So the question here is, okay, we saw a glimpse of these concepts working, but can we actually put them to the test? Do we have case studies? All right, so what I'm going to show you are 2 case studies that my group has worked on, one in Italy, one in Andorra. Okay, we have boots on the ground there, and they both feature different, so they both test different aspects of the model, if you like. So the first one is the Ruinion landslide, which is a bit west of the Vajont, still in Italy. I don't know if you can see, this is Milan up here. This is the study area. It's at the borders with Switzerland, very close to Lake Como. You know, all this for science. For science. What can you do? Okay, so the interesting part is that this is a very deep and steep valley. There is a river at the bottom of the valley, and it features a number of landslides. So our case study is here, but there is one next door. So with this one, the good thing is that we had topographic maps. We had GIS, access to GIS maps that we could download and reconstruct them into a finite element model, and then actually do the proper elastoplastic study that gave us 2 results. So what we did is this is the finite element result. It doesn't look like it, but it is, using my code, Redback, down here. Okay. So what we did is we matched observations. So this is a map of the plastic strain. Okay. So we are expecting a landslide here. We are expecting a landslide here. We matched that, and then we got the stresses, the dependence of the stresses with respect to different groundwater level as a bonus. Okay, so that was our matching process. So once we have that, we can start working the model. Okay, so we have the stresses, we have the water pressure, we have tons of data from the site, we have piezometric levels, we have velocities, we have everything. Okay, so and we also have material from the site. So we could take the material and actually test it in a thermal triaxial and get the rate sensitivity with 3 points, 4 with 0. Okay? He was right, by the way. And the thermal sensitivity. Right? So we have everything. We can constrain the model pretty much exactly. Okay? And for the students here who, we are in an AI and data-driven approach and probabilistic. When you have the physics right and you can measure everything, you should have a deterministic inversion. Okay? That's how you know that you have the physics right. So let's do that. We take that as input, the groundwater level. We feed it in the model. This is the velocity over time. We use part of the velocity to tune the value of the Grunfeld number. Okay? And then we forecast. When Andrea Morcioni saw that, I think he was done. Like for a week, he didn't come back to the lab. He was celebrating when he saw the forecast. I'm not kidding. Okay? So when we did that, then you can map it on the phase space. And the landslide lives here, which when we saw that, that was a bit too close for us. All right? So you can see it's very close to the instability. So Andrea went, and I had to go as well for science to Lake Como. And we talked to the agency, and they did drain the water out. So they opened the borehole and drained the water and brought the landslide somewhere around here, which is until today. Okay, the model spits out the evolution of the temperature at the shear band, okay, as well as a bonus. But the real test is the inversion. So I told you, we need to do the inversion. We have all the properties. Okay, so the inversion is as follows. The model has one parameter, the Grunfeld number. However, this parameter is a parameter group. It has all the properties in there, okay? So we know this value because we tuned it here. We know these 2 values because we measured them in the lab, okay? We know this value because it's the initial condition of the velocity. We know that this is the thermal conductivity. We measured it in the lab. It's 0.5 joule per Kelvin meter second if you're, worried, okay? So we kind of know the stress from the finite element simulation. It's not constant. There is a band because the sliding surface is not at the same depth. Okay, so there is a band between, I think, 250 and 400 kPa, depending on where you are on the landslide. And we also kind of know the thickness of the shear band, although it's very hard. This one is very hard to determine exactly, but it is between 5 and 15 centimeters, depending on where you sample. Okay, so we can actually plot this expression. We chose to plot it for different values of thermal sensitivity. We know the thermal sensitivity, and this one passes exactly through. All right? So case closed, the model works. You can do a deterministic inversion. These are the physics. But we haven't tackled that dinosaur here, that skeleton in the closet. Okay? The model spits out temperature evolution at the sear band, and every sane geologist, geological engineer, or civil engineer will say, are you out of your mind? Are you nuts? All right? Like, how do we even assess that, and what does it mean? Exactly is my answer. Exactly. Okay? So these are the remaining questions. How do we measure that, and what does it mean? Is it even having an effect on the process? Is it real? Okay? Further than that, what is the rate and thermal sensitivity on the friction law even means? Like, what does it represent? Like, what are we talking about here? Okay? What is it? Okay? And the third one is, do we even need all these things? Do we even need thermal sensitivity? Like, why are you bothering us? Okay, I hear you. I hear you. So here's the second case study. This is a case study in Andorra, the L4 landslide. This is essentially a field lab for my group. We have very close collaboration with Barcelona, the UPC in Barcelona, and the government of Andorra. And we have installed sensors, monitoring, et cetera, et cetera. So here is the landslide. The landslide sits on top of, I don't know if you can see it, city of Canillo, which is 5,000 people. Okay? This is the dream of every civil engineer and the horror of every policymaker. You have that on top of a city. So we don't want that to fail. Like, there is no room for error here. Okay? So this one, we drilled a borehole. You're going to see it in a second. Okay? This is the inclinometer at depth. So this one is the closest example that you will ever see on a rigid block sliding on top of a shear band. All right? There's a shear band around 30 meters down. You cannot fake that. This is the only example I have ever seen in my life that this is a rigid block. Okay? All right. So we do have access. Well, we actually drilled the borehole. Okay? Not we. We were there. Okay? We have installed piezometers, thermometers, et cetera, giving us continuous measurements every 20 minutes since 2017. Okay? And we also have retrieved the core logs from the site. Okay? And you can see here the shear band has a distinctive clayish nature, like it stands out. Okay? So what we did first is we took samples at different depths, so inside the shear band, outside the shear band, far outside the shear band, and we did mechanical testing and microstructural analysis. All right? So microscale analysis comes first. What you see, oh, you cannot see it's okay. No, sorry. So this is the mineralogy. They are essentially kaolin-like clays, so lots of muscovite, lots of paragonite, lots of quartz, and they're all the same in depth. They're all the same, okay? And what we could distinguish in terms of deformation and fabric orientation were three groups. The first group, in terms of deformation, the first group is outside the shear band, the rigid block. There is no deformation here. And the microstructure, the fabric, is randomly oriented. There is no obvious orientation of the fabric, all right? There is scattered all over the place. Then, right outside the shear band, whatever you want to call that, we call the damage zone. Okay, there is a zone where the fabric starts organizing itself, the porosity drops a bit, but it's not still fully aligned. All right? Don't try to think in terms of alignment with respect to shearing direction. We couldn't do that. We couldn't infer that because these are thin sections. We don't know how to correlate it. All right, and then you have the shear band in the middle, fully aligned microstructure. Fully aligned microstructure, increasing porosity, still same mineralogy. All right, so these are the three groups, and then we took samples from all three and we tested them in our high pressure, high temperature triaxial at Duke. We may have had to invent some new protocols in testing because we didn't have enough samples to do proper tests. So we have mixed and matched standard testing on the outside material, which we had a lot, with what is known as isotac, I believe, test, like velocity stepping and temperature stepping on some materials, okay? Because we didn't have enough material and we couldn't remold them. We could remold them once, okay? After the first remolding, the material was collapsing. It was impossible to even test it. So the results are in terms of rate, sensitivity, all the materials had the same rate sensitivity, and I have more than 2 data points. Right? So all the materials inside the shear band, outside the shear band, rigid block, they all had the same rate sensitivity. However, when it comes to thermal sensitivity, there was a distinct difference. The material that is undeformed with chaotic or with random microstructure was significantly less sensitive as opposed to the shear band. Okay, so what you see here is a shear stress or friction coefficient, right? So that draws the natural conclusion with respect to what are these mechanisms representing, is that rate sensitivity essentially represents the mineralogy and is controlled by the mineralogy, which we kind of know for clays. And thermal sensitivity is a proxy for dissipative processes in the fabric, related to the fabric orientation. Okay? That's, we were satisfied with this. All right, now, next level. Let's analyze the field data. I promised you temperature measurements, and you're going to be disappointed. All right, so this is in depth, the same plot of the borehole. The shear band is here. We have installed 3 thermometers, 1 above, 1 below, 1 in the shear band, and we have also, and you can see them here, the shear band thermometer below the shear band, above the shear band, normalized to their initial value. And we also have piezometers in the same locations. Okay, so this is a dry, unfortunately, a perched aquifer. There is a pressurized aquifer below the shear band from all the snow melt collection, okay, which is here. And the one in the shear band never returned any readings. The shear band is dry. Okay, well, dry, not dry, but it doesn't have pressurized water. Okay, and we also have readings of the incremental and cumulative displacement. Now, I know what you're thinking, so let me take it out of the table. Seriously? So this, we are talking about an evolution of less than 0.01 degrees Celsius. Okay, so first of all, this is above the reading sensitivity of the instrument. Let me reassure you about that. So this is real signal. But is it even important? Who cares? Okay. Now, I need to say that this is a very small period of time that we didn't have major slip events. So we do have a case that I cannot show you where the temperature spiked half a degree in a day and we had an acceleration. But for obvious reasons, I cannot report that. Now, the interesting bit is despite its low value, there is a diabolic correlation between that and that. All right? You don't see it easily here. You'll see it on the next slide. But what is happening is that any fluctuation of the water pressure below the shear band, okay, is reported or recorded within a few hours, let's say 12 hours, in the temperature inside the shear band. The temperature of the aquifer stays constant. There is nothing here. Okay? So you see this blip here, this is recorded here, and then a day after that, we have a velocity acceleration. Okay? So this is counterintuitive. You would think a different order, but this is because this one is hotter than the shear band. Warmer, not hotter. All right, so we have all the data we need to answer questions. And the question I wanted to answer is, who cares, basically? Okay? Do we even need to consider these complicated effects with this low value of temperature? And what do we lose if we don't? Okay, like what do we lose? Why are you bothering us? All right, Vardoulakis, go away. We don't need that. All right, so the nice thing here is that because we have the temperature reading, we don't need to tune the Grunfels number. We can tune the Grunfels number here directly on the temperature and then forecast the displacement. Okay, without knowing anything about the material. Now, we did it with and without thermal sensitivity, and we had equally good fit. Okay, so seemingly we don't need thermal sensitivity at all to accurately reproduce the field data. Okay, we don't need that. By the way, this is what I meant. This one is the pore pressure, and the other one is the temperature sensor. You see the direct correlation between the two. All right? Now, so we don't need that. I was wasting your time for the last 43 minutes. We don't need thermal sensitivity, all right? Or so we think, all right? So if you are now, and that is a side note, and I don't want to single out a discipline, but I will. So if you are a machine learning enthusiast, you see that and you say, I don't need anything, all right? I take data and forecast data. I don't need physics because you just wasted my time, all right? So I say, hear me through, all right? The truth is in the pudding, and the pudding is the inversion. So here is the inversion, same inversion I did before. We know the thickness of the shear band. This is an inhomogeneous landslide, so we have a larger variation of the shear band thicknesses depending on where you sample, between 20 and 40 centimeters. These are the stresses, okay? And these are 3 inversions done without thermal sensitivity, with the thermal sensitivity of the shear band. So all the deformation is on the shear band, and without considering a shear band. Okay? So let me explain it plain and simple. If you ignore thermal sensitivity, in order to get the same results in the same shear band, you need to significantly overestimate the stresses. All right? You need the shear band to be, instead of 30 meters, at 1 kilometer depth to have the same results, the same observations. Okay? So if you don't, and you actually have the physics correct, you do a deterministic inversion. Everything checks out. Okay? So that's the first. The second reason that you need thermal sensitivity, I'm not going to waste your time with that, is the following. If you don't have thermal sensitivity, your model is unconditionally stable. There is no softening mechanism. Okay? There is no softening mechanism. So you may be able to fit. We go back to the same argument that we had at the beginning. You may be able to fit creeping segments of the landslide, but you will never predict the transition. Okay? Now, the problem with physics and the cares of modelers, so you need thermal sensitivity to accurately explain the physics. The problem with forecasting failure and preventing it is that if you prevent it, no one will believe it was there. Okay? Deal with it. It's fine. Now, as I'm going towards the conclusions and the outro part of the discussion, this is the question that I was asked a few years ago, 4 years ago, from my then incoming PhD student, saying, okay, given enough in-situ data, you can verify the physics. Fine. But you will never have enough in-situ data. All right? We don't have natural labs, field labs popping out everywhere. Okay? So can you do something with sparse data? Okay? So this is where you can go and start peeling off some physics. If you understand that you have the right physics, you can start, watering down a bit. All right? So this is the Mud Creek landslide. This happened in California in 2017. This is the one that brought the Highway 1 down, okay, for those who are from the area. It's up here. Now, this one does not have any in-situ monitoring. All the data we have are from remote sensing, okay, from the satellite. And the guys in JPL, they're very smart guys, and they were able to give us velocity and pore pressure time series inferred from satellite data, okay? So we did the same trick, same thing, okay? Took the groundwater data as input, tuned the Grunfeld number to fit the model data up to and including failure, and then mapped it on the phase space. The phase space is here, where you see it just came out, okay, and failed a few days before failure. So I cannot give you, this is the case where I don't have a deterministic inversion. If I do an inversion here, it's going to be probabilistic, and there is no way I can give you useful feedback. Like if you ask me, okay, so what is the depth of the sliding surface? I don't know. I can tell you between 0 and 100 kilometers. That's going to be the distribution I'm going to get. However, you can still use it as a real-time monitoring and assessing tool. Like if you were the engineer in the field and you have real-time information and you are somewhere here, you will run to go and drain the landslide, okay? And what is best is that you also know where to go. Okay, so I'll show you how. So you can use the same tool to provide. So this is my infamous student by now who asked the question, Rachel Lowe. She ended up doing a PhD. So who's laughing now? Okay. So this is the same exercise we did with a single point in-situ measurements, but with a field, right? So this is the velocity coming from INSAR, from the satellite. Okay, we use that together with some precipitation data from satellite and weather input, and we did the same, but for a field. We tried to match the velocity field this time. And when you do that, okay, fair enough, this is Andorra. It's a very simple case because it is a rigid block. Okay, you can then go back to the model and generate a Grunfeld map. This is a Grunfeld map, and I guess that by now you know that larger values of Grunfeld mean more unstable areas. So if you have to go and operate somewhere, you will go there. Okay? So this is how you handle uncertainty a bit with the physics to get what you need, essentially. Right? So in closing, I don't have conclusions. I have run over time already. I'm going to close with the statement of my infamous now student, Rachel, when she finished her PhD, where she clicked and said, there is no way around. Okay? In order to mitigate the effects of disaster, you need to understand disaster. There is no way around that. Okay? There is no easy free lunch, free meal solution. Okay? So with that, I would like to thank you, and I'm open for your questions.
Yeah, thank you, Manolis. Very nice presentation. Yeah, I have a question that I think I had understood maybe differently, but is there a second coupling of the temperature and the pore pressure? So do you have,
Yes.
because you have clay, so you have very low
Yes.
dissipation of pressures?
Yeah. So I already went like 5 minutes over, so I didn't have time to include that. But so let me show you if I can. Okay. Here. All right. So the idea of this model, maybe. No. All right. So the idea of the model I presented, okay, is going from creep, from critical state all the way to tertiary creep. Okay. Once you are in tertiary creep, so when I said that it goes to thermal runaway, nothing goes to infinity. Okay. So the explosive increase in temperature and velocity stops, is mitigated by triggering at higher temperatures thermal pressurization. Okay. So you can see it here. So this is the early version. There is a more sophisticated model now, but same concepts. Okay. So essentially, pore pressure is 0 until this term kicks in, and this term kicks in at the very late stages of tertiary creep. Okay. So if you like mathematical representations, this is very inefficient. Okay. So there is no way in physics, in reality, that there is an uncapped increase in temperature. Okay, you cannot admit temperatures like higher than the sun. So in reality, there is a third branch here that you go and rest, which is a dynamic weakening, which is a thermal pressurization. All right, but this is a very late effect. So that's the point I wanted to make. Okay.
So you don't include in your model this second term of this pressure?
Because I'm only interested in going
in the first part.
Yeah, in the first part. Okay, so I do have the work for also like the full.
But this is a stabilizing parameter.
Well, it depends on what you mean by that. Mathematically speaking, yes. Okay, but this is where maths and engineering differ. Okay, that mathematically speaking, this gives you a stabilizing factor, but that's already too late for engineering. It's the stable solution is a dynamic weakening and acceleration, like at essentially full inertia. But that's stable, yes, mathematically.
Okay,
yeah.
Thank you.
Well, by the way, sorry. In that case, you can do the same with other materials, not clays, that admit, instead of thermal pressurization, you have a different phase change. Like I have done it with carbonates, where instead of thermal pressurization, you have carbonate decomposition, capping. this thing. So instead of thermal pressurization, you have a chemical reaction generating fluid and lubricating. It's the same thing. This is for faults. Yeah.
I want to challenge your statement about we're never going to have enough data. I
Yeah.
actually have seen too many fields in my life that went from data poor to data rich because of the ability to measure more and more things.
Yes.
My question to you is, if we could have some sort of device we could sprinkle in various places,
Yeah.
what measurements should we be taking?
Yep.
Is it just displacements?
No.
What measurements should we be taking? Let's say if we have, because many of these places we knew
Yeah.
there's sliding going on.
Yeah. Yeah.
So maybe what we need to do for our mitigation is
Yes.
more field
So,
measurement.
you don't have to challenge me. I agree with you. The statement I made is for areas, remote areas, like what I showed you, or areas where the population is impervious to in-situ measurement, like the Josimath. That's a holy place for the tribe that lives there. You cannot go and measure anything. What do you do? So anyway, to answer your question, I have been trying to minimize, to find the minimum, the global minimum of what to suggest. Okay, and I think in terms of both cost and efficiency of, okay, if we get this data, we make a step change, is very simple. Just put thermometers in the boreholes that you already have piezometers, but put them also in the sear band. Okay, so that's far more cost to info effective than saying, do exploratory boreholes everywhere and give me the core logs. Okay, that doesn't hurt either. But you understand that the thermal sensor like we installed that, which is a high precision sensor for $150. Okay, and it's the borehole, like we would already drill the borehole, and the borehole can also serve as a drainage. So that's probably the most cost effective. Okay, now Rachel Lowe, the one that the student that did the remote sensing, she also has, so that was her PhD. It was not just generating hazard map. She has an optimizer that can tell you from satellite data, saying, okay, these are the areas of the most uncertainty. If you drill boreholes, go and drill them there. So you can use that tool to inform where you drill boreholes. In fact, her first paper came out officially today, and that's the title. Okay, INSAR informed monitoring of the field application. So you can use that to minimize. Depends on what you minimize. If we minimize cost for a given information, that's what I would say. Yeah.
Ladies first.
So I may have not understand the presentation correctly, but you'll see according to my question. Is that possible that there might be another variable that fills the same equation as the temperature does, and that would be responsible for, the sliding?
Can I call you Eduardo Alonso? Because this is the discussion I have with Eduardo. Yes.
Oh.
Yes.
Oh, okay.
So mathematically speaking, sorry, are you done? Can I? Okay. So this is the question I was expecting, and thank you for asking. Go. All right. So mathematically speaking, the answer is yes. Okay. So what do you need? You need a reaction diffusion equation. You don't even need an exponential. Any nonlinear term will do. Okay. And you need a nonlinear term that is nonlinear, a reaction term that is nonlinear with respect to your variable. So obvious candidates are the pore pressure. Okay, you could substitute temperature with a pore pressure, or could you? So the question is, this is where physics come with maths, because I have a model that I have a model where this is extended to include pore pressure. Sure. The question is, what are you trying to model? And that was a discussion I actually had with Ioannis. And he was very, when he had an idea and he was fixated, Like there was no argument. So, and he's right, eventually, 20 years later. So he said, we need a model that can capture critical state. What is the definition of critical state? constant volume, constant stress ratio, so constant porosity. There is no pore pressure, and unlimited shear. What is the only field that can change in unlimited shear? The shear dissipation. This is the only thing that can change, that he was fixated. Now I told him, no, you can have damage accumulated. He said, yes, but that's coupled to shear deformation. So my honest answer is, mathematically speaking, yes. I gave you the ingredients, all right? This is the easiest approach because this is a governing law. This is not just a governing law. This is the governing law. And the bifurcation I mentioned, this one, maybe. This is not a random bifurcation. I brushed through it superficially. This is a dissipation function. Okay, so what I'm telling you here is that the dissipation function has a saddle point. The system self-organizes at not a maximum of dissipation before. That's what I'm telling you. So this is the discussion. The discussion becomes philosophical now. Is yes, you can use any equation. The question is what that equation should be, and how do you measure what you put in? That's it. Because what I said, like the temperature is a proxy of dissipation. It's not. I'm not saying that you should be measuring temperature everywhere. Okay? If you have a better, I had this discussion with my friend in Australia, Itai Einav, and he said, why don't we measure grain size evolution? I said, yeah, sure. Grain size evolving would change the temperature. Sure. Can you? So that's my answer, which I know it's not satisfying, but this is where I am as well. If you have a better idea, I'm open.